first of all, I would like to thank the organizers for giving me the opportunity to present these results, and I would like also to acknowledge our collaborators for this project, so in particular Miriam Barry and Zul Bandier at the Simon Fraser University for the synthesis of the material and the characterization, and also our collaborators from different neutron sources, so in particular Brillouin, Zurich, Peter Gehring, and William Radcliffe at NIST, Karen Schmatzel and Frédéric Bourdaro at DRL, and Bertrand Rosely and Tom Fenner at PSI. So I'm going to talk about the presence of both lifetime shortened acoustic phonons and the static order in the hybrid halide perovskite. So the hybrid halide perovskites have attracted a lot of attention recently because they have been identified as promising materials for photovoltaic and optoelectronic applications. So in particular, it has been shown that devices made of these materials show power conversion that can exceed 20%. So this family of materials can be described by the well-known ABX structure. So in this case, the A site is occupied by a molecule. So in this case, it would be methyl ammonium, but of course, it can also be another molecule is formamide diphenyl. The B side is a metal, so it can be lead or tin. I'm going to talk about the lead. And the X side is occupied by halide ion, so it can be either iodine, bromine, or chlorine. So the lead atoms here are located in an octahedral environment that is formed by the halides. And these octahedra share corners to form an inorganic framework or cage. And at the center of the cavity, you have the molecule. And this molecule is linked to the inorganic framework by hydrogen bondings. And I should also mention that the cage size can vary depending on the nature of the halides. So, for example, the iodine has the biggest atomic radius, so this would give the biggest size for the cage, and the chlorine has the smallest radius. So the size of the inorganic framework can also influence the strength of the hydrogen bonding. So like many other perovskites, these materials undergo several structural transitions. So these are the different sequences of transitions that are found in these three materials. So as you can see, at room temperature, both bromine and chlorine compounds are cubic, while at room temperature, the iodine compound is already in its tetragonal phase. So the phase transition between the tetragonal and cubic structure is actually at a higher temperature. Also, the bromine compound shows an additional tetragonal distortion, and some studies actually show that this phase can be maybe incommensurate. And the chlorine compound also shows a narrow tetragonal phase. So all of these structural transitions consist of tilt and distortion of the inorganic octahedra, but there's also an order disorder transition of the molecule. And it has been shown that this transition happens at the orthorhombic transition. So many experimental and theoretical works have been devoted to understand the molecular dynamics in this system. So for example, in the bromine compound, quasi-elastic neutron scattering have shown that the molecular dynamics follows a sequence with two steps. So at low temperature, the molecule is in its static order, and it starts activating around 50 K, and between 50 K and 150 K, the molecular dynamics consists of rotation of these amine and methyl groups around the carbon-nitrogen axis. And above 150 Kelvin, there's another step which corresponds to the full rotation of the molecule. So there have also been many studies, in particular with Raman infrared spectroscopy, which allow to identify the many rotations, movement, and vibrations of the molecule in its dissolved state. And also it has been shown that although the molecule doesn't directly affect the electronic band structure, its coupling to the inorganic framework through acoustic phonons can affect the mobility and the lifetime of charge carriers, and also the thermal transport. So I'm going to mainly focus on the chlorine compound, and I'm going to talk about the inorganic framework dynamics, and I'm going to show some results that have been obtained by means of electroelastic scattering. So this is a photo of a cold triple axis spectrometer. So this is TASP, which is located at the Swiss neutron source, PSI. So during a scattering experiment, you have the sample that sits in the cryostat, and you have an incoming neutron beam with an incident wave vector. So you can define this wave vector by the rotation of the instrument around this axis, and then you can define the final energy and wave vector thanks to the rotation of the instrument around this axis and rotation around the axis of the analyzer. So the scattering experiment is constrained by the laws of momentum and energy conservation, and it allows to probe excitations in the reciprocal space, but also as function of energy. So we have measured two phonon modes, two transverse acoustic phonon modes in the HK0 scattering plane. So the first mode that I will call TA1 was measured around the bright peak 200 and towards the X symmetry point. And the second one, which is TA2, was measured around the 220 bright position and towards the M symmetry point. So the TA1 mode corresponds to an acoustic phonon that propagates in the direction of 100, and its polarization is along 010 or 01. And the TA2 phonon corresponds to a phonon that propagates along 110, and its polarization is along 1 minus 10. So we have measured these two phonon modes first in the cubic phase at room temperature. So these are constant Q scans that were copied on the thermal triple axis IN22 at the ILL. And we have completed the measurements towards the low Q regime on spins, which is a cold triple axis of NIST. So what you can see on this constant Q scan is, first of all, a broad incoherent scattering that comes from the hydrogen cross-section. And on top of this background, you have well-defined phonon modes. So by extracting the energy position of these modes for each Q position, you can get the dispersion for these two modes. And the slope of TA1 is related to C44, the elastic constant C44, and TA2 is related to this elastic constant. So in this table, I just summarize the elastic constant that were extracted in the iodine and bromine compound, and these are the values that we have extracted in the chlorine compound. We can also extract from this the phonon line width as function of Q. So the phonon line width is related to the inverse of the phonon lifetime. So what is striking here is that you have a strong broadening of the phonon towards the zone boundary. And this is the most dramatic towards the endpoint. What it means is that you have a significant shortening of the phonon lifetime towards the zone boundary. And in the cubic phase, the molecule is in its disordered state. So what it shows here is that this damping may be caused by the fast molecular dynamics that is coupled to the inorganic framework. It's also interesting to compare this to the all inorganic counterpart. So this is cesium lead bromide, which has the same structure, except that you have a cesium ion on the A site. And in this compound, we also have measured TA1 and TA2. And again, we can see a strong damping or a strong broadening of the phonon modes towards the zone boundaries. And again, it's also it's the most dramatic around the endpoint. So a Raman study that was coupled to calculations have also shown that the A site developed strong fluctuations and strong anharmonic vibrations. So we think that this phonon broadening actually arises from the fluctuations of the A site. And this is interesting because this shows that this phenomenon is not just unique to the hybrid systems. So we also followed the temperature dependence of these phonon modes. So these are constant Q scans that were taken near the zone center. And what we can see is a sudden increase of the energy position of this phonon mode, which indicates a sudden hardening of the phonon branch at the orthorhombic transition. And this goes along with a bump in the phonon line width just above the transition. So this indicates that you have a shortening of the phonon lifetime just above the transition. In parallel, we have also tracked the quasi-elastic scattering as function of temperature at the zone boundaries. So these are elastic scans that were measured at the X point and the N point as function of temperature. So what we can see is that there's a sudden jump, a sudden increase in intensity at the orthorhombic phase transition. And what is also striking is that the line width, the energy line width of this scattering remains resolution limited for all temperatures. So what we can see at high temperature here is an energy line width that corresponds to the instrumental resolution that is extracted from incoherent signal of a Van standard. And at low temperature, it drops to the Bragg resolution of the instrument, and this is associated to the delta function in energy and momentum. So I also want to mention that in the orthorhombic phase, so at low temperature, the molecule is in its ordered state. So the appearance, the onset of this scattering at the low temperature transition is associated to the ordering of the molecule. So now, if we look at the elastic scattering as function of temperature, so we've measured the elastic line at different zone boundaries. So what we can see is the onset of new Bragg peaks at the R and M X points when we go from cubic to tetragonal phase, and then the onset of the endpoint at the orthorhombic phase. So X and R become symmetrically equivalent in the tetragonal phase, so that's why they turn on at the same time. And according to neutron scattering structure factors, the R and X points represent dispersive distortions of the octahedra, and the M point represents rigid tilt distortions of the octahedra. So again, if we compare to the all inorganic compound, we can see that in this system there's a different sequence of transitions. So it's actually the first, the endpoint turns on the first, and then it's followed by the R and X point. So this shows that in the hybrid system, it's this classic distortion of the octahedra that occurs the first, and that is favored by the tetragonal transition. So now, if we summarize all of the results, we've seen resolution limited, an energy resolution limited signal that increases at the orthorhombic transition. So this was at the zone boundaries. And in parallel, we also saw a sudden hardening of the phonon nodes near the zone center, along with a jump in the phonon line width, also above the transition, so just above the transition. So this shows that there's a coupling between the dynamics at the zone boundary and the dynamics at the zone center. And the dynamics at the zone boundary is associated to the molecular dynamics, and this is associated to the inorganic framework. Also, these are associated to two different time scales. So this is especially evidenced by the jump in the phonon line width here. So I'd like to discuss a little bit more about this figure. So the fact that we see this central component that is centered around equals 0, and also the fact that we don't see any critical fluctuation, we don't see any fluctuations in energy that is temperature dependent, and that will show any critical behavior. So this feature has also been reported in other perovskites, and in particular the strontium titanate compound, in which they report a simultaneous softening of the phonon node at the same time as the onset of this central component as function of temperature. So several theoretical models have been developed to explain the presence of this narrow central component, and they explain this by the coupling between 2 degrees of freedom. So in our case, the particular structure of the methylammonium chloride system allows us to understand and illustrate this coupling between two different dynamics and 2 different time scales. It has also been shown in the relaxer ferroelectric, so PRN. So in this work, the dynamics associated to the diffuse scattering coming from polar nanoregions has been probed by neutron backscattering and also neutron spin echo. And what's interesting here is that these 2 techniques allow to probe dynamics with timescales that are less than the gigahertz. And while the backscattering data will only show a static nature of the scattering, the neutron spin echo techniques allow to separate this static component from dynamics here. So in order to check if we have actually a critical dynamic scattering in our system, further measurements with high resolution will be needed. So what's interesting in these systems is both the presence of an order-disorder transition,